Hello everyone. Today we have gathered here to hear me talk about how machine learning algorithms hear. I know it's a bad pun or a joke, but today we are going to discuss about how machine learning algorithms can hear audio. So before we start off, a quick introduction about me. So I'm Abdul. I'm an inventor slash data scientist. I'm currently working for Data Robot, who is into automated machine learning. Previously, I was in Microsoft, and before that, Computer Associates. And just something that is quite common with me. So, a couple of times when I don't, even after someone has repeated it thrice, if I don't hear them, I just smile and nod. So, if I'm smiling and nodding, and if it's a question, just come closer to me and talk. Yeah. So, let's start off. So, what are we, what, why, and how? So, essentially, what are we trying to do here, and why we are trying to do here, what we are trying to do, and how we do it. So, essentially, audio processing, we are trying to process audio using machine learning algorithms. The ability to process audible data like voice, sound, speech is what we are trying to achieve. Once we are able to process this data, we will be able to classify, segment, or generate new audio. So this is what we are trying to achieve. Why we want to do this? If you see, there has been a rapid spike in signal processing applications like voice-based assistants, machine transcription, sound classification. So all of this has in the recent times just spiked up. This is not new. This has been tried before, but with the advent of deep learning and all of the other uh, 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 machine learning advancements, we have seen a lot of rapid growth and demand in processing audio data sets also. Earlier, audio storage was also not available, so audio was not captured to the extent that we wanted. But now with cheaper storage, we have so much data that has flooded our ecosystems that we are now mining data out of audio, which seems to have given us like a lot of advantages, and that's why we are doing this. How? There are a couple of approaches that we use to do audio processing or mine data from audio. So these are like simple. The simplest way is structured feature engineering. Convert your audio files. If you have 100 audio files, how can you convert it into a data frame of 100 rows and X columns? So once you have that data frame, you could use any of the traditional uh, algorithms like random forest, gradient boosting, any logistic regression to process through them. Then we have the multi-dimensional feature engineering. So in this, you convert your 100 audio files, for example, into 100 n-dimensional arrays. So once you have those n-dimensional arrays, you could run convolution neural networks on them. So, and then you can use that to either classify segment or classify segment or regress your data. Temporal feature engineering, this is more time-based engineering. So if you have seen the advancements in time series, so time series signal processing, what we do is for each point we take a stock of what are the previous 40 or n steps, what were the values, and the next 40 or n steps, and we use that to train in a temporal fashion, and use that to classify or segment or regress over the signals. So here what you try to do is you convert your 100 files into 100 rows or more rows of sequence data, and then you run a recurrent neural network on top of it. So these are the three common ways, depending on which way you apply, or depending on a problem statement or your accuracy standards or acceptance criteria, you could use one of them. So, any questions still here? Quickly, just on the what, why, and how. of audio mining using machine learning algorithms. Okay. So before we jump into further details, what are some of the applications that we are seeing, the real-time applications currently in the industry that we are seeing for audio mining? So the most important or most impactful application of audio mining right now, which deals with very close to conservation, because this is something that deals with nature, humans as species. We are using this for bioacoustics. So audio mining in bioacoustics is used for uh, identifying species, identifying ecosystems, how they work with minimal intrusion, right? So without capturing animals, you can monitor animals, birds and species, without having to intrude into their into an ecosystem. You can just monitor them. So that's where a lot of bioconservation or species conservation efforts are using audio mining to identify, segment, count different number of count species that are available in a closed ecosystem without totally intruding into that ecosystem. All researchers are now able to just put mics in key points in the forest and record audios, and then use that to identify whether a species, the number of species of a particular, the population of a species is reducing, increasing. Are we finding new species that we have not even uh, identified yet? So that is one. That is some of the things that we are doing on this side. The other one, which is quite familiar to everyone, voice-based assistants, Siri, Google Now, Alexa. With the growth of these assistants, there is an assistant for every possible application right now. So this is where audio mining is being used for, because a lot of human speech is used in these assistants. YouTube transcription, if you have seen nowadays, you could see the closed captions or the captions under YouTube videos. They are no longer something that you need to type, they can be automatically generated. Even Skype or Hangouts allows this. So while you're talking, your audio is being transcribed, and later you could use that for minutes, or referring back to what was spoken, or as compliance documentation. The other place where audio mining is being used nowadays, which is a bit niche, but it is just gradually picking up, is music generation or audio generation. So people are generating music using frameworks like Google Magenta, which uses an advanced form of recurrent neural networks to learn over a data set of music and then generate new music, and that is being used by artists to generate new art forms, so that they could there are, if you go and find on the internet, you will find a lot of artists are now moving to generation of music using, they have the lyrics but they don't have music. So what they do is, like, they generate music using Google Magenta. They feed in a lot of files of the genre that they want to sing for, and then they get the music, and then they use their lyrics. So if you are interested in generating music of your genre, you could go ahead and play around with Google Magenta, which is like a higher level abstraction library which can easily generate music. You just need to give it data and it will do it. Or you could play around with recurrent neural networks, as we will see in this demo, and generate your own music also. So audio mining, just a brief introduction about it. It's not rocket science. It's just signal processing. We have been doing signal processing for a long time now. This is nothing new. Only there are advancements in storage, advancements in processing that have given us technologies like deep learning and all that allow us to do more. As I said, it's not new. Time series processing has been it has been done for decades now. So Similarly, audio mining has also been done. Only thing is like newer and newer advancements are helping us do more and get better models or accuracies or churn more data. You can audio mining is similar to text mining. You can just it's very analogous to it. So for ease of understanding, you can definitely think of it very in terms of how you do natural language processing. And if you are conversant in natural language processing, it is going to be very easy for you to use audio mining. Different approaches for audio mining. So here, like I said earlier, there were three approaches that I had hinted to. I'll go down and show. I'll uh, talk to talk about those approaches in terms of text mining, so that you could easily understand how it is very similar to text mining. So first thing, structured feature extraction. As I said, you want to convert your 100 audio files into 100 rows of a data frame with n features. So this is similar to term frequency inverse document frequency in text mining, right? So you convert your text into a matrix, and then you use one of those algorithms to it. So the first structured feature extraction is similar to TF-IDF. Multidimensional feature engineering or extraction is similar to embeddings. So you have seen a lot of embeddings being used for NLP. So like BERT, Google or Yahoo embeddings that you could use. So what you could do is like wiki embeddings. So once you have these embeddings, you can run convolutions on top of it. So similarly here for audio also, what you do is you convert these audio files into images of spectrograms. So we'll talk about it. So once you convert these audio files into images, you could use images or n-dimensional arrays. You can use convolution on top of it. Temporal feature extraction. So once you have text encodings, you could use recurrent neural networks, or you have text sequences, you can use LSTMs and GRUs, which are recurrent neural networks. So same thing, we'll use recurrent neural networks on audio files also to generate new audio. So these are the approaches. This is audio mining in a nutshell. Any questions still here before we jump into each approach in depth? So first things, structured feature engineering. How do you convert your audio files into a data frame with fixed columns? So the traditional or the most fundamental way that people have been doing for a long time is Fourier decomposition. So what you do is you take a signal, you decompose that signal into a bunch of standard waves or standard signals. And once you have those standard signals, you do this using Fourier transform. And once you have these standard signals, the coefficients of these waves or signals will be used as your independent variables. So it's simple math. It has been done for a long time. So early speech to text algorithms use Fourier transforms a lot. So for example, Windows Phone had the SDK. If you go to Windows Phone SDK, you could use, if you go into the SDK and want to use the speech to text capability, it will use Fourier transforms to decompose your odd words into Fourier transforms, and it does a lookup in an index and brings the word which you have spoken. So this is one of the oldest techniques, or the easiest techniques to start off with. And the advantage of this technique is you don't have to use specialized algorithms. You can use your random forest, gradient boosts, XGBs. You could use logistic regressions. You could use decision trees. So on top of this, so support vector machines. Any of your traditional regular vanilla algorithms can be used with this technique. So a bit deeper into what Fourier transforms are. Fourier transforms are essentially, if you look at this wave, so what Fourier transform does is it converts a signal from time domain to frequency domain. So if you see this signal, it is essentially a signal on the time domain. So as time progresses, what is the amplitude and what is the amplitude? And now what we are trying to do here is we are decomposing this wave into into the frequency domain into two waves, as you can see, the red wave and the green wave. So the green wave is the cosine wave and the red wave is the uh, red signal is the uh, sine signal. And if you see, when you add up these both signals, you will get this uh, resultant our uh, our signal that we started off with. So once you have this, what you do is like you take the coefficients, which is a and b, and these form the columns in your data set. And for each file you will try to do this, and you will end up with 100 rows of 2 columns, and this is how you get that data frame. So as you can see, we have converted 100 mp3 files into a data frame of 100 rows with 2 columns, given this example. But generally it is not too so we generally go with 125 or 129 coefficients roughly. So this is how we use Fourier transforms. As I said, it is quite easy, simple, and runs on almost all of the algorithms that we have right now. So any questions on Fourier transforms right now? Okay, let's go to let's walk through some code and see how we do this. So this is an example where we have around 25,000 mp3 files, and each of the file is tagged with one or more of labels. So you would have a audio file in which there is a tag of traffic because there is traffic noise. There is a person who is crying, so it could be traffic with a person or human. And there is like uh, a chopper going on top of it, so which is like a chopper. So you can have it's a multi-label multi-class and multi-label problem. So more than one label can be attached to each file, and we can see how we can solve this using the first structured feature engineering method. So the library that most commonly is used is Librosa. SciPy, which is scikit learn, also has scientific Python also has uh, library has functions for processing audio. So you have something called SciPy dot audio, if I'm not wrong. But yeah, SciPy also has similar functions which you could use. So Librosa and SciPy are the most common that we use for audio processing. So as you can see, this if you see, we have around 25,000 files. There are labels. These are labels are like space separated label, multi-class and multi-label values. And folder is like which folder do we want to pick up the file from. So we do not in practical sense in practice we do not only use directly Fourier transform. What we do is we use a derivative of a Fourier transform, which is called MEL frequency subsystem coefficients. So what MFCC, which is short for MEL frequency subsystem coefficients, is first we take the Fourier transform of the signal or the audio file, and then we convert that into a MEL scale, which is like a logarithm of logarithm of the MEL of the Fourier transforms, or the powers of a spectrum. It's it's a normalization of the Fourier transforms, and then on top of it we put a log, and then we do a cosine transform, and then we get MFCC. The reason we do MFCCs is it has two functions. One, it reduces the number of Fourier transforms, which could be too large, and also it does a normalization effect on it. So we get two advantages of it, and it is like the standard stuff. It kind of MFCC also isolates different audio signals within a file into neat little subspaces. So that's why we use MFCC. So here this is some stuff. As you can see, what we are doing here is like we are using multi-threading. So multi-threading to load the files. So as you can see, I'm loading a file, and then here I'm capturing from that audio file what are the MFCCs. I'm extracting the MFCC. So MFCC number we can give, typically 125 should be a good number to start off with, most basically. And yeah, so this function will get us that, and it takes us around 50 minutes roughly for 25,000 files. These are files with around a few with a median length of 3 to 4 minutes, and audio clips of 3 to 4 minutes median length, and we are able to load it in 49 minutes or 49 minutes. And yeah, so we can see here, once we have done that, we have, for all the 25,000, we have 129 features or the independent variables. And now since we have this, we can just load this into any of our algorithms. We can just attach the label to this data frame and then load it into any algorithm that we are interested in and run it and get. So here we are doing some feature engineering on the label, because as I said, multi-class and multi-label. So we have 81 different labels that are the tags that we can tag these audios on. So for each of the file we have gotten this. Now once we have this, we can use this. So if it was a binary classification or a multi-class classification, this would be one this would be one column. But since here we are having multi-class and multi-label, we are taking 81 because we want to be able to use there will be multiple classes, so we want to use algorithms that could process multi-class and multi label outputs. So once we have this, now we do a scalar. We do our standard pipeline, which is use our validation methodology. So here simply I'm using train test split for sake of time. Here I'm using a neural network because I have 80 output columns, so which just for ease of use, we could use multi-class, multi-label outputs from scikit-learn algorithms also. But just for ease of use, I'm using a neural network. I'm using binary cross entropy, and my metric is cosine proximity, just to see how it does. And this is my simple neural network that I'll use to process this structured data. And yeah, so as you can see, the loss has been decreasing. So at this point, it seems like my model is no longer able to explain the variance. So there is it ends up overfitting. So I know that with this data set, I could probably get this kind of loss. So beyond this, I'll need some extra features and all of that. But this is overall, and the label average ranking precision is this. So this is how we can play around with structured frequency. As you can see here, we have taken 25,000 audio files, MP3 files, and then we converted them into 25,000 rows of 125 columns of a data frame, and then we are using an algorithm to process that. So these are the 81 features that they are. So microwave or earth. So this is how we use structured feature engineering. So any questions on this till here?